All right, raise your hand if you were able to figure out this problem of the day. All right, this is good. One thing I will say about second term, more so than first term, is this relies a lot on teamwork. That means if you figure out a step, don't give the answer to a partner, but explain it to them. You're going to learn a lot more by working in a group than you will trying to solve all of these on your own. I sent you guys out an email last night with the hint that you should try to work backwards with these problems. So the first thing we need to do is we need to figure out how are we going to make a ketone and an aldehyde. And in the email, I give you guys a big hint. What was that reaction? Ozonolysis. So step 1 would be O3. Step 2 would be zinc and water. And this would rely on us having an alkene that looks like this. All right, so now the question becomes, how can we make an alkene? E2 elimination. All right, there's a couple different E2 routes we could have taken for this, but the easiest route would have been to have some sort of halogen on there. I know some of you actually had an alcohol and did E1 elimination too. That's fine. There's oftentimes more than one correct answer. So what reagent or what base should we use for this E2 elimination? Strong base? Okay, so let's use just sodium hydride for fun. Why won't I use terbutoxide? It would create the Hoffman product. So just like we covered last term, we have to choose the size of our base to get the alkene that we want. We don't want to get our Hoffman alkene. All right, now we've got to figure out how can we get a bromine installed in this position. So we've got a couple different alkenes we can go off of. We've got this alkene, or we could have this alkene. Which one do you think's the more appropriate alkene? Yeah, the top one. The bottom one, we're just kind of running around in a circle a little bit, so that doesn't help us very much. But if we have this alkene, we can do hydrobromination. Let me clean this up a little. And we can just react this with HBr. Remember, hydrobromination will add your halogen to the Markovnikov side of your alkene, not the anti-Markovnikov side. What if I wanted to get a bromine off of this blue carbon? What reagent would I use? Yeah, hydrobromic acid and peroxide. In this case, we want it to go in that green position, so we'll just use plain old HBr. And then we're almost there. How can we get from our starting material to this alkene? Yeah, strong base. Strong non-nucleophilic base. What happens if we use a nucleophilic base? We might get substitution. So let's just change up our base and let's use DBU, diazo bicycloundecene. That was one of our non-nucleophilic bases. We could have also used DBN. We could have used sodium hydride. Any sort of non-nucleophilic base would have worked for that reaction. Otherwise, you might run the risk of getting a little bit of SN2. On the first exam, I'll give you guys a practice exam, but you will be required to learn how to do synthesis problems this term, and we're going to practice it a lot. But it'll be a lot of problem solving like this, where you have to piece together how to get from a starting material to a desired product. Make sense? Yep.
Isn't the DBU kind of large for that tag?
It is. You could use sodium hydride. There's only one beta proton available, so it only has one thing to grab, and you could heat this up really hot and get the elimination to go. Yep.
What if on that last step with the ozone, instead of using zinc and water, you used DMS?
Yeah, would work too. Any sort of reducing agent would work for that last step. Yeah, there's oftentimes many different routes and reagents you can select. It makes your guys' life a little bit easier and mine harder because I have to grade it. All right, so let's cover our last reaction for Chapter 9. Last reaction for Chapter 9 is catalytic hydrogenation.
Do we have to memorize all the names of it?
I'm not super interested in the names, but I want you to know what reagents are needed and what the transformation is. So catalytic hydrogenation is a unique reaction where you take hydrogen gas and you seal it in a vessel with your alkene, and you typically add some sort of catalyst like platinum or palladium, and typically this catalyst is on a carbon substrate, so it's not just a chunk of platinum in there. That would be a very expensive reaction. So you pressurize your vessel with hydrogen with a little bit of catalyst, and then you shake it up. That hydrogen will get absorbed by that alkene, and you end up forming an alkane. The main thing to remember with this reaction is that your hydrogens add to the same face. They don't add anti, they always add syn. Yeah. Does anybody know one of the main industrial purposes or uses where this reaction takes place? Think of food.
Oh, trans fats?
Yeah, trans fats or hydrogenated oils. So if you think about fats from vegetables are typically unsaturated, meaning they've got some sort of double bond in them. And I'm just going to make up a fat. Typically they're triglycerides. And then when you do this reaction on an industrial scale, you can take that double bond and convert it into a single bond. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8. There we go, 9. Why would we do this reaction?
Cheaper?
It's cheaper, and if we think about unsaturated fats, are they normally solids or liquids? Liquids. So vegetable oils are commonly liquids. When we hydrogenate it, we turn that alkene into an alkane, and we can turn it into a solid fat. This was a really big deal during World War II when there was a worldwide shortage of dairy fat. And so chemists during that time frame realized we can take a bunch of vegetable oils, hydrogenate them, and make Crisco, right? So many of you use Crisco in cooking. What's the downside with this reaction? It's unhealthy. Saturated fats typically aren't very good. Does anybody know the byproduct of this reaction?
What is the PD?
One thing you might notice is this alkene is cis or trans? Cis. During this hydrogenation process, oftentimes you get some of your alkene where it actually switches around and forms a trans fat, and you don't get full hydrogenation, and that's where you hear the term trans fat thrown around a lot. That's the byproduct of a hydrogenation of a vegetable oil, typically. Yep.
Will the trans fat be liquid as well?
Trans fats are often liquids. When they do hydrogenation reactions like this with vegetable oils, typically it's incomplete hydrogenation because they don't want it to turn into like a wax. They want it to be semi-solid. And so that's why you often have a little bit of trans fat in there as well. Trans fats, they're finding out more and more, are terrible for you. And this is why people are trying to get away from hydrogenated oils in foods. So that's just my side comment on hydrogenation.
So where did the double bond go? Did it turn into a hydrogen bond?
No, the double bond now has these two hydrogens added onto it and turned into an alkane, right?
Yeah.
So it's not that we did anything with the true carbon-carbon bond. We just added hydrogen into that pi bond.
Oh, okay.
Yeah.
So do trans fats occur in nature?
Not normally. There's some plants that produce a really, really, really small amount of them, but our bodies aren't designed to really manage them very well, and they cause heart disease. On a side note, too, this is just getting into my, I don't want to call it politics, but there's been a lobby by the food industry to label things as trans fat free, even though they contain up to 5% trans fats. And that's why you should often look on food labels to see if there are any hydrogenated vegetable oils in that product. What's that?
They do it with sugar too.
Yeah, with sugar. It's one of those things where the vegetable oil lobby got involved and was like, hey guys, it's not very much, it doesn't matter. And it's like, well, it does matter, it causes heart disease. All right, so let's take a look at one of these reactions. There's actually a variety of different catalysts you can use. You can use platinum, you can use palladium, there's even some new nickel catalysts. And what will the product look like for this reaction? Well, remember, in this case, we'll have the methyl group going back. We'll have our hydrogens adding across the double bond syn to one another. Is there an enantiomer we have to worry about for this? Not for this example. Why not? It's meso. But the main thing to remember is that these hydrogens always add in syn to one another. These sorts of catalysts are called heterogeneous catalysts. And heterogeneous catalysts are a fancy word for catalysts that don't dissolve in solution. They stay suspended. But there are some other reagents where they do dissolve. So let's take a look at a different example. This one we're going to use hydrogen gas. And we're going to use a more exotic catalyst. This time it's going to be a ruthenium catalyst with a triphenylphosphine ligand coming off of it. Oh, sorry. This should be pH 3 bracket and then 3 on the outside. And this will give you a similar product. So this would be called a homogeneous catalyst.
What makes that homogeneous?
So homogeneous, if a heterogeneous catalyst doesn't dissolve, what do you think a homogeneous? Yeah, it dissolves in solution.
But like, if we were treating the problem, how do you know the homogeneous?
The ruthenium one with all of the ligands coming off of it is going to be your homogeneous catalyst. We don't see it very often in the Klein textbook, and you don't see it very often in normal synthesis. Did you have a question?
Yeah, what is your medium? I mean, wouldn't that depend on what?
Oftentimes you have an alcohol solvent. So it's, in this case, your ruthenium catalyst would dissolve in the alcohol. It wouldn't stay suspended as solid particulate matter.
So, I mean, doesn't like, if it's heterogeneous or homogeneous, doesn't that depend on the medium? Or
A little bit. Inorganic metals really don't dissolve in any solvent.
Oh.
Yeah. Why do you guys think we might use this really exotic ruthenium catalyst? Does anybody have an idea or guess? To show off that you're a chemist? Do you think with the platinum, palladium, or nickel that you get very much selectivity with which face of the alkene you add those hydrogens onto? No, they go after any face of any alkene that's available at all. These heterogeneous catalysts will oftentimes exclusively favor one face of an alkene. So the reason I wanted to bring them up is you may occasionally see them, especially if you go on and take advanced organic chemistry, but they can be used to add H2 to only one face of an alkene. Oftentimes when they do this, they end up changing this triphenylphosphine ligand to some ultra exotic ligand that's chiral. That way it can only approach one side of the alkene and not the other side. But for our class, we're typically going to see platinum, palladium, or nickel used in examples. They're a lot easier to remember. One nice thing with this is we don't have to worry about the mechanism. The mechanism's an inorganic mechanism, and it actually occurs at a surface interface. You can read the book in a little bit of detail on it, but even the book doesn't go into much detail on this reaction. Yep. Which one?
So if we're answering like if we're given a problem like this, do you want us to show only one product? Like, is there?
If there are a set of enantiomers or a set of diastereomers, I want you to show both.
But you just said that these homogeneous catalysts can be preferential. How would we know?
I wouldn't expect you to know. You would have to be a very, very experienced chemist to be able to predict that.
Okay, so we'll still put both of the enantiomers?
Yeah.
Okay.
Yep.
So you said ruthenium, right?
Yep.
But isn't RH rhodium?
Or is it? I'm completely blanking out right now. Wilkinson's catalyst is, yeah, I guess it's rhodium. I don't know why I wrote ruthenium. Sorry.
Okay.
Yep.
So do we add to the phase that is more substitute or less?
For platinum and palladium, it'll add across both equally. So we'll take a look at an example, and I'll show you guys what to watch out for with this reaction. Do you have another question, Ramon? Okay, you're just chilling. All right, let's take a look at an example. Let's say I've got this alkene where we've got a methyl group that's a wedge. We've got a methyl group coming off of our alkene, and we're going to do hydrogen gas, and we're going to use palladium on carbon as our catalyst. We're going to pressurize this and shake it up. What product or products might we get out of this reaction? You'd get two products. So let's draw out the two products we would get from this reaction. This top methyl group was untouched. It's not on that alkene. But we could have one product where our hydrogens add in as wedges, meaning these methyl groups will be dashes. Or, shoot, the methyl group's down here. Or we could have one where those two hydrogens add in as dashes. What's the relationship between these two compounds? They're diastereomers. So just like with all of these addition reactions, we have to watch out for stereoisomers, specifically diastereomers and enantiomers. Diastereomers once in a while pop up, but normally what we're observing is a set of enantiomers. All right, so that's our last reaction. But what I wanted to do before we go into some more practice problems is go through kind of a review guide for this chapter. So a concept review. Because there are a few key things that I wanted you guys to remember from this chapter. The first one is Markovnikov versus anti-Markovnikov. So if we have an alkene, we're going to have some sort of addition of H, and I'm going to call H blue, and I'm going to call the other portion A, and I'm going to label it as red. All right, if it's Markovnikov addition, where is the hydrogen going to end up? Okay, let's think about this. Where's the H going to end up? Less substituted, right? Because our A, whether that's a bromine or something else, is going to end up on that more substituted side, and this H is going to end up on that less substituted side. So this would be Markovnikov addition. That means our substrate's always adding onto that more substituted carbon, and the hydrogen's going to be on the less substituted carbon. Or the alternative is that our hydrogen adds to the more substituted side and our other substrate adds on to the less substituted side, and this would be anti-Markovnikov. Yep.
Because H is, could be like smaller than 8.
It has to do with the reagent choice. So we can control Markovnikov versus anti-Markovnikov addition depending on what reagents we use. So let's take an example, and I want you guys to help me predict whether or not the reaction is going to give you the Markovnikov product or anti-Markovnikov product. How about hydroboration oxidation? So that was with BH3 THF. We had a peroxide in there. Anti-Markovnikov. So hydroboration oxidation would be anti-Markovnikov. Oop. That would install an alcohol on this A position. What if we want the alcohol to be over here instead? What reaction is that? So what if we want Markovnikov addition of an alcohol? Does anybody remember?
How about
Acid catalyzed hydration. So these are closely related, but they install alcohols on different positions. So acid catalyzed hydration. All right, what about oxymercuration demercuration? That was our other reaction where we could install an alcohol. Does that install the alcohol in the Markovnikov position or anti-Markovnikov position? Markovnikov. Why would we use oxymercuration, demercuration? No rearrangement, exactly. Demercuration. All right, let's say I want to install a halogen like bromine, and I want it to go Markovnikov. What should I use? I want to install a halogen instead of an alcohol, and I want it to go in the Markovnikov position. What reagents do I need? It's halogenation, so we just use hydrobromic acid, so we could do hydrohalogenation. Specifically, without peroxides. That means we could do the anti-Markovnikov addition with peroxides. So we've got two different ways to install alcohols and two different ways to install halogens. So make sure that you're comfortable identifying the addition as being Markovnikov addition or anti-Markovnikov addition, especially for the quiz coming up. All right, you guys ready for the next review topic? Is it okay if I scroll up?
Just a second. What's the difference between an alkyl O and alkyl?
Oh, W/O is shorthand for without. W without that O just means with. So if we want anti-Markovnikov, we have to do it with peroxides. If we want Markovnikov, we have to do it without peroxides. All right, the next thing we have to do is we have to look at syn versus anti-addition. And this specifically refers to stereochemistry, not regiochemistry. So let's say we've got this alkene. This time we're going to add X and Y. So I'm going to label X as blue and Y as red. We could have one where they add to the same face. So we could have Y over here, and we could have X over here. And we could also end up with an enantiomer, assuming X and Y are different. Would this be syn or anti-addition? Syn addition. Or we could have it where they install on different faces. So we could have Y, for example, as a wedge and X as a dash. And again, we would end up with a mixture of enantiomers here. So this would be anti. With these guys, it really depends on your substrate, but for this example that I've shown, you would get a mixture of enantiomers. All right, so now we have to try to identify the reactions that fall into each class. So I'll start out easy for you guys. Anti-diol is going to give you what? Anti. What reagent do we need for anti-diol? Does anybody remember? It was an acronym? MCPBA. Followed by an acid workup. Okay, so that gives you anti-addition. What if we want syn-diols? Or syn-dihydroxylation? I should be calling these dihydroxylations, sorry. Yeah, osmium tetroxide, followed by some sort of reducing agent. What was the reducing agent we used? It was sodium bisulfite to reduce off that osmium. We didn't need to know the mechanisms for those, but they're closely related. They just alter, or they differ in the stereochemical outcome. All right, the next one. What if we use Br2 and we do a bromination? Will that give us syn addition of bromines or anti addition of bromines? Anti. So bromination with Br2 is always going to install those bromines anti to one another. Yep.
So does that say 0504 or?
Right here.
Oh no. So OS04?
Yeah, OS04, so osmium tetroxide. All right, so bromination's anti. What about the halohydrin reaction where we're installing an alcohol and a bromine?
Oh, that's syn.
Is it syn or anti? Ah, there's some disagreement. It's just like bromination, but the water outcompetes that bromine from adding across, so it's still anti. So halohydrin reaction. Yeah. Is that good? Okay. So that's Br2 and water. All right, let's see which ones we're missing right now. What about hydrogenation, the one we just covered with hydrogen gas? Does that do syn or anti? Syn. So hydrogenation. That's when we have something like H2 and platinum or palladium. All right, so let's see if we're hitting them all. What about hydroboration oxidation? Does anybody remember that one? That one was tricky. Was that syn or anti? Syn. So hydroboration oxidation. And I'm going to make a little note here. And I'm going to say with respect to the hydrogen. So the hydrogen that gets added in hydroboration oxidation will be syn to that alcohol that's also added. So that's another strange one. So let's see if we've got them all. I've got 1, 2, 3. 1, 2, 3. I think that's the main ones for syn versus anti-addition. The last topic I wanted to cover before we do a handful of practice problems are ring opening reactions, which again is related to stereochemistry. And we saw a handful of ring opening reactions this chapter. So I'm going to give us a generic example. And I'm going to call the ring head Z. And it's going to be a 3-membered ring because that's the only ring size we've seen. And I'm going to have just 2 methyl groups hanging off there. And in all of these, we had a nucleophile attack our ring. Which side was attacked? Was it this side on the left, or was it this side on the right? The left. The nucleophile will always go after your more substituted side of your alkene. Specifically, it's going to attack underneath and ring open this. So our final product will have 2 methyl groups sticking up, and it will have a nucleophile right here. And then the Z will add right there. So if we think about what Z was, we had one where we had bromonium, so the bromine was stuck in the 3-membered ring. What other elements did we have in the 3-membered ring? What was that? Chlorine could work. So, what was that? Oxygen. So we had epoxides. That was where we used MCPBA and we protonated it. So this could be, I'm going to call this OH. What else? Mercury was our last one. The main thing to remember for these reactions is that the nucleophile will always attack the more substituted carbon if Z has a positive charge. We're going to cover that when we get into our ether chapter and talk about epoxides, because if we don't have a positively charged member in the ring, we actually get a different stereochemical outcome. So this is a big if. But in this chapter, we always see that Z with a positive charge. The other thing to remember is that we invert stereochemistry, or stereocenter, at attacked carbon. So this nucleophile, when it adds in, is doing a reaction that's really reminiscent of an SN2 reaction, right? It's coming in from underneath, and it's kicking off a leaving group. That means the carbon that's getting attacked is getting inverted. Does that make sense? Scroll up. So the nucleophile, that blue thing, when it attacks, is attacking from the underneath side, and that carbon where it's attacked gets inverted, just like we saw that inversion of stereochemistry in SN2. Just like SN2. Exactly. All right, so now let's take a look.
So even if the nucleophile is really large, it'll still prefer the more substituted side?
Yeah, in the addition reactions in particular, we almost always see that nucleophile attack the more substituted side. All right, so now I'm going to show you guys one really nice thing in the Klein textbook. At the end of every chapter, he has this summary of reactions. This is a really, really valuable tool for studying. What my students did last year was they would go through, photocopy this, and then white out the reagents that were needed. So if you actually go through my notebook, I've done this for you. And you can turn this, you can turn this into a fill-in-the-blank sort of study guide. And you can print this out over and over again and just practice the repetition of writing down those reagents. That way they stay fresh in your head. Other times people would do flashcards where they would have the starting material and the reagents, and then on the back they would put the product, or they would have the reagents and the product, and on the back they would have the starting material. That way they could just cycle through remembering the transformations. This especially gets valuable when we get into chapter 10 and 11 and 12, and the stack gets bigger and bigger and bigger and bigger. Just seeing them regularly is a really, really big help. So try to use these study guides in the back of your textbook. But let's go back to the summary of reactions. And there were a few reactions where you didn't have to know the mechanism. So I'm going to label these. You don't need to know the ozonolysis mechanism. That wasn't one I cared that you knew about. The other one is the syn dihydroxylation with osmium tetroxide. You don't need to know that mechanism. The other one you don't need to know is this one. You can skip directly to the epoxide. I don't expect you to know the mechanism for the formation of the epoxide. The other one you don't need to know the mechanism for is hydrogenation with the hydrogen gas. The other one that is super tedious and I don't expect you to know is hydroboration oxidation. And then the last one is the oxymercuration demercuration. So you do have a fair number of reactions where you do need to know the mechanism, but a handful where you do not need to know the mechanism. So you may want to make a note of this in your textbook or in your written notes, and then try to practice the mechanisms for all of the other ones. Does that make sense? All right, so I've got some practice problems that we can work on with the remainder of our 5 minutes. So let's go back. And the good thing is these practice problems are actually out of your book. So if we don't have time to cover them all, they're really good practice problems to go over. So let's start with 9.50. So that's problem 50 from the back of your book. And what I normally do with addition reactions is I ask myself first, is it Markovnikov or anti-Markovnikov? If that applies, then I ask myself whether or not it's syn or anti-addition. So let's start with this one over here. We've got BH3.THF, got hydrogen peroxide, and we've got sodium hydroxide. Is this Markovnikov or anti-Markovnikov? Anti-Markovnikov. So what side of the alkene are we going to add to? Less substituted side. So we could say, well, we're going to add to that side of the alkene, and what are we going to add into that less substituted side? Are we adding in a bromine? Definitely not a bromine. An alcohol group, right? So hydroboration oxidation installs alcohols in the anti-Markovnikov position. So we can go through and we can say, all right, we could have the alcohol get added here. Is this our only product? What would our other product be? Yeah, the enantiomer. So if we think about our other product, we could have one where that alcohol is a wedge or a dash. So we have to account for both of those. So for this reaction, we end up with a mixture of enantiomers. All right, let's do the next one. We've got Br2. We can't consider this Markovnikov or anti-Markovnikov because we're not adding in a hydrogen. But is it going to be syn or anti-addition? Anti. And we're going to add in 2 bromines. But why am I not showing the other bromine with stereochemistry as a dash or a wedge? It's not a stereocenter, so we don't have to worry about drawing a dash or a wedge when we're not dealing with stereocenters. So for this one, we would end up with this, and it's an enantiomer. All right, hydrogen gas and palladium, or platinum, sorry. What will that do? It'll be syn addition, and it'll change the alkene into what? An alkane. So these are super easy. I don't even have to draw in the hydrogens unless I really want to, right? The hydrogens are assumed, and we don't have any stereochemistry in this molecule. All right, the next one, we've got HBr. Will that do anti-Markovnikov or Markovnikov? Markovnikov addition. So if we think about Markovnikov addition, it's going to add into the more substituted side of our alkene. And do we have to worry about forming a mixture of enantiomers? No, because again, there's no stereochemistry in this molecule. A lot of people would say, well, what about this stereocenter? It's not a stereocenter, right? You have the same path going around one side of the chain as the other side of the chain, so there's no stereocenter in that position. All right, what does MCPBA and peroxide do? It's going to be anti, and it's going to install two of what? Two alcohols. Oop.
Is the M usually lowercase?
It's normally lowercase. Occasionally, the Klein textbook, he's not consistent with it, though. All right, so we could have an alcohol here. We could have an alcohol here. Do we have to worry about a mixture of stereoisomers? Yes. So I'll just write plus EN underneath. The other really nice problem for practice that we won't have time to get to is problem 71 from the back of the chapter. This time you have to pick the reagents, not the product. So you can kind of use this as a rough practice guide for the exam, or not exam, the quiz. The quiz will have fill in the blanks and likely a mechanism problem. It'll be about the same length as our quizzes last term. Yep. All right, if you guys have any questions, I'll be around tomorrow morning.